Okay, let's dive right into this drone-level flight over Unit 2. If you're a first semester BCA student, this is where things get incredibly exciting. This is the exact moment we take all that pure, abstract math we learned and literally transform it into the physical hardware that powers, well, every computer on the planet. Remember all those Boolean algebra equations and K-maps we spent so much time on in Unit 1? You might have been wondering, okay, but what's the actual point of all this? Well, here it is. We're taking that Boolean algebra, grabbing those simplified K-maps, and using them as the actual blueprints to draw the physical circuits. We are finally moving from the world of ideas right into the world of silicon. So, our roadmap for this unit covers 5 totally manageable chunks. First up, combinational logic, focusing on adders. Second, we'll meet the flip-flops. Third, designing sequential circuits. Fourth, routing with digital components. And finally, registers and binary counters. All right, let's hit section 1. Combinational logic, the adders. Think of combinational circuits as living entirely in the present moment. They just do math based on the inputs you're giving them right now, with zero memory of the past. The most fundamental math, of course, is addition. That brings us to our very first building block, the half adder. It's actually elegantly simple. It just uses an XOR gate to calculate the sum of 2 single bits and an AND gate to figure out if there's a carryover. It does exactly what it says on the tin. But it has one major limitation. It's called a half adder because it cannot accept a carry-in bit from a previous addition stage. So how do we fix that? We literally click 2 half adders together. You connect them with an OR gate, and boom, suddenly you've got a full adder. Because this full adder can accept a carry-in, we can now chain them together in a long line to do multi-bit arithmetic. This right here is the true foundation of a processor's calculator. Moving right along to section 2. Meet the flip-flops. See, a computer that only adds in the present moment isn't all that useful, right? We need a way to actually remember that math and store data. That introduces our foundational memory elements called flip-flops. Under the hood, the most basic memory circuit is the set-reset or SR flip-flop. It uses cross-coupled gates, where the output of one feeds directly into the input of the other, to indefinitely hold a state of either a 1 or a 0. It's basically your digital memory baseline. But early on, engineers realized the SR flip-flop had a fatal flaw. It has a crash state. If you try to send a 1 to both the set and reset inputs at the exact same time, the circuit's logic just becomes undefined and totally breaks down. So here's the crucial takeaway. You should view each new flip-flop on this table not as some brand new confusing concept, but simply as a bug fix for the previous one. Think of it like software updates. The D flip-flop fixes the SR's crash state by making sure set and reset can never be the same value. It just safely stores whatever data you feed it. Then the JK flip-flop takes that invalid 1-1 crash state and brilliantly turns it into a feature, causing the output to toggle instead of crashing. And finally, the T flip-flop simplifies the JK by creating a dedicated counting mechanism that just flips its state on every single clock pulse. Now, before we can go building complex circuits with these, we need a special design tool called an excitation table. Think of it like a reverse engineering cheat sheet. Instead of asking, hey, what happens if I input these signals? An excitation table asks, okay, I want the memory to change to this specific state. What inputs do I actually need to force that to happen? Which brings us seamlessly to section 3, designing sequential circuits. So how do we actually take these concepts and build real memory hardware? Well, this flow right here is exactly how hardware engineers design sequential circuits. It's this gorgeous logical progression. You start by visually drawing out the behavior you want. Then you map that drawing into a state table. Next, you use those excitation tables we just talked about to calculate the required inputs. And finally, you apply the K-maps that you mastered back in Unit 1 to shrink that logic down into the most efficient hardware circuit possible. And here's what that very first step, the state diagram, actually looks like in practice. We're graphically tracing the exact behavior of our memory circuit from one state to the next using these circles and arrows. Each circle is a memory state, and the arrows show how the clock pulse pushes the circuit forward. It's essentially a flowchart, but for hardware. On to section 4, routing with digital components. Okay, so we can do math and we have memory. Awesome. Now we need to package these concepts into pre-built, integrated circuit chips to route our data around the computer. This is where you'll hear terms like SSI, MSI, LSI, and VLSI, which just refers to how many microscopic gates are crammed onto a single chip. We're going to treat these next few components like digital flashcards. First step is the decoder. A decoder takes a small binary input and expands it, activating exactly one corresponding output line. Say you input a binary 3, well, output line number 3 lights up. In the real world, these are often built using NAND gates to keep manufacturing costs down. Now, if you understand a decoder, you already understand an encoder. Encoders are quite literally the exact functional inverse of decoders. Instead of expanding, they squish. They take multiple input lines where only one is active at a time and condense them back down into a super concise, readable binary format. Next, we have the multiplexer, which everybody just calls a MUX. You can think of the MUX as the ultimate digital traffic cop. It has several lanes of incoming data, but only one exit lane. It uses dedicated select lines to choose exactly which one of those input signals is allowed to travel through to the single output line. It literally controls the flow of information.
And finally, Section 5, Registers and Binary Counters. Let's see this in action.
Let's look at how we take all of these pieces, the flip-flops, the logic gates, the routing components, and chain them together to do practical work. We already know a single flip-flop stores just one tiny bit of data, right? A 0 or a 1. But a computer needs to store whole numbers, text, instructions, the whole shebang. Enter the register. A register is simply a whole squad of flip-flops working together, listening to the exact same clock pulse to store multi-bit values all at once. When you hear people talk about a 32-bit or 64-bit computer, they are literally talking about the size of these registers. A really cool variation of this is the shift register. By cascading those flip-flops in a line, the data bits can physically slide to the left or slide to the right on each and every clock pulse. This sliding action is absolutely crucial for things like digital communication, serial data transfer, and even performing super quick multiplication and division right at the hardware level. Our final stop on this architectural tour is the synchronous counter. Remember the T flip-flop from earlier, the one that toggles its state? Well, by wiring a sequence of T flip-flops together so they all share the exact same clock signal, they toggle in perfect unison to count upwards in binary. Because they're completely synchronized, they avoid the delayed, cascading lag you'd normally get in a simpler, cheaper ripple counter. So I want to leave you with this thought. By understanding how to combine adders, flip-flops, multiplexers, and counters, you aren't just memorizing definitions for a test. No way. You now possess the complete fundamental hardware alphabet required to build literally any computing processor in the world. The only limit from here on out is just how many gates you can fit on a tiny piece of silicon. Keep exploring that, and I'll see you in the next explainer.